Hello? Oh, man. DPDPD. Oh, maybe I should repeat it from the start again. So far, I've beaten the defeated and finished Teacher's Priority Queue, backtracking tries trees, when I searched the with stack two pointers, and arrays and hashing, and so far, I'm almost about to finish graph, but it's a hard problem, so I'll have to skip it and do DP first before finishing graphs. I'll probably do bit manipulation. It's kind of critical. And maybe I want to learn more about advanced graphs and intervals. The greedy algorithms in the school as well. Yeah. Word breaker. Given a string S and the dictionary of strings, word dict. Return true if it can be segmented into a separate space, separate sequence of dictionary. You are allowed to reuse words in the dictionary. You assume all dictionary words are unique. Turn the true list into them speaking to neat and from Apple Pen app. Return true because Apple Pen, okay? Apple Pen and app. Necessary and also not use all the words. What? Ah, pen, eat. What? Can split. Cats, cat, sin, in, car, cars. What? This is false. If, but it's, what? You can use it. Given a structure fit can be segmented as space areas dictionary. Oh, there's, well, that's because it can be separated. This one is not a word. Bro, I don't get it. What? I don't get it. These things are extra. You can't should get but then I'll pick a word for it. Let me just a question. So we continue behind it. You need to determine the reconciliation. The basic condition is that they're true if um, should call with index I iterating through S to check all the words in order to and recursively processing grabbing I by the length of mashup and a recursive pattern is immediately. However, this solution is exponential. Can you think of an optimum? Maybe you should consider an approach that avoids repeated work. You can avoid recursive and for your class, we're using memoization to iterate with index I. You can use a hash map or an array of the same length as S, cache the results of cursive calls, and prevent redundant connect computations. So memo calls an array of empty strings. Oh no, multiplied by S file, right? One that's forgot what the syntax is it like this. And it seems I don't get this shit, bro. How would you know if it's if it's a word? Maybe I need to watch a video.
Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem word break. So we're given an input string and a dictionary of strings called word dict. And we want to return true if and only if S can be broken up into separate strings such that every separate string in S is also found inside of our word dict. And we are allowed to use words from the word dict multiple times. So for example, let's say we're given an input string leetcode, and we're given a word dictionary of words called leet and code. So obviously, in this case, we could split this string, right, into separate strings, leet, right, break it down in this middle position, and then the second string would be code, right? So clearly, this can be broken up into words that are found in the word dictionary, so therefore we are going to return true. Now, what if we took code outside of our word dictionary? Well, then in that case, this portion, leet, is a word, right? But we have no matching word in our dictionary for the remainder code. So in that case, we would have to return false. And, let's say we had an input string instead called leet and leet again, right? So two leets in a row, would we return true? Yes, because we're allowed to use this word from our word dictionary multiple times, right? Clearly it matches this, and it also matches the first portion. Now let's start off with the brute force approach. How would we even structure a brute force solution? Well, there's actually two ways to do it, but one of them happens to be more efficient, and I'll tell you why. So one thing.
So the string is cats and cars, and the only available word dicts are cats, sin, and got. It's false because car can't was cars. There's a missing S. Can't separate this. And this one, apple, pen, apple. Yeah, and you can use your word all words and also not use all the words in the dictionary. Ah, okay, I get it now.
Hey, we could check, okay, the first character, right? Basically, the first prefix of this string, L by itself, right? Is this a word that's found in our word dictionary? It's not, right? So let's try maybe the first two characters together are a word, right? That's not it either. We would try the first three, right? Basically, we would try every single portion from the beginning until we found a matching word that does exist in our word dictionary. And we know that we are going to find one like this, right? The first four characters of the string are a word, right? So once we found that, what are we going to do? Clearly, we have a sub problem, right? We found a matching word for this portion, but now we want to know, can we break up the rest of this string with words from our dictionary? So that's kind of how we're going to do it, right? That's what's going to be the sub problem, basically. So instead of starting from the first position in the string, we would start at this position in the string and try to word break it. Now, in this approach, what we're going to basically be doing potentially is from every single starting position, right? We're going to check every prefix, right? So from the first starting position, we might also get, if this happened to be a word, then we would start at this position and then do the same thing for this, right? Every word starting here. So basically, we're going to try every word. How many different words are we going to end up trying? We're going to try, let's say n is the size of our string n, and we're going to try basically from every single starting position to the end. So that's going to basically be n times n. Now, we could also do it a different way. Instead of trying every single possible, prefix, let's just check every word in our word dictionary and see if that matches. For example, this first word is 4 characters long, right? So what we're going to do is we're going to check the first 4 characters in our string. Does this match this word? Clearly it does, right? So what does that tell us? That tells us now, we have the same subproblem as before. We're going to start from this next position now, right? And check. And from here, we're basically going to be doing the same thing, right? So we're going to check, is leet basically, the first 4 characters, does that match leet? This does not match leet, right? So now
Thanks.
let's check the next word in our word dictionary and check, does that match the
Less than
characters over here? It
98
does, right? We
solution.
found code. So this is basically another way to do this problem. Instead of checking every single possible prefix, right, of any length, what we're going to be doing is we're going to be checking every single word in our word dictionary as the prefix. So instead of being O of n times n, we're going to be doing O of n because potentially we are going to be going through every single starting position, but we're going to be multiplying by the number of words in our word dictionary, which is, let's call it m. And the reason why we're going to be doing this approach is because it's going to be a little bit more efficient. And the reason is they tell us below in the problem statement that the max size of word dictionary is going to be smaller than the max size of the string. So this is overall probably going to be more efficient. Now, this isn't going to be the overall time complexity. We are actually going to multiply it by another n, because when we're checking, for example, this string, when we're checking, does that match the first four characters here? That's also a n time operation, because it could, potentially be the size of the input string s. So this is basically going to be the overall time complexity, n
Nah.
squared multiplied by m. So I'm just going to basically show you the same formula that I usually do. I'm going to give you a quick illustration of what the decision tree would look like. Then we're going to understand how we could cache that to eliminate repeated work. And then by understanding that, we're going to go to the optimal dynamic programming solution, the bottom up approach, and then we're going to code that up. Usually the DP solution is a lot less code than caching. So we're going to be looking at our
Wow.
input string neetcode. So I think that's a little bit better than neetcode, wouldn't you say? So what the decision tree is going to be is we're going to start at the first position, right? For example, I equals 0. We're going to be keeping track of whatever index we're at, right? Because we know that if we can find a word, that matches neat, for example, then the subproblem is going to be, finding words that can match the remainder of the string. For example, if we did that, our I, instead of starting at index 0, would basically be starting at index 4, right? So that's what the subproblem is going to be. So really, we're only going to have one variable that we're keeping track of in this backtracking solution. And so remember, we mentioned we're not going to be doing it like this. We're not going to check every single prefix. We're going to have decisions in our decision tree based on the number of words that are in the word dictionary. So we're going to have a decision for neat, we're going to have a decision for leet, and we're going to have a decision for code. Now, what we're going to notice is when we try leet on here, right, basically leet is 4 characters, therefore we're going to check the first 4 characters of here, compare it. Does that match leet? It does not, right? We're just 1 character off, that first one. So basically, that means we're not going to continue down this path. Now, let's try code. Does code match the first 4 characters? Definitely not. So we're not even going to continue down this path either. Of course, neat does match this, so we are going to continue down here. We're going to do 3 more decisions, basically 1 for every single word in our word dictionary. Now, one thing though is when we are starting here, we know we matched the first 4 characters, so by this point we are now going to be at I equals 4, meaning we're going to be looking at this part of the string. So as we can see, checking neat, that's 4 characters long, so let's check 4 characters starting from here. That's not matching, of course, so then we're not going to continue here. Leet, does that match over here? Nope, we're not going to continue down this path. Code, does code match this portion? Yes, it exactly matches. So therefore, we are going to update our I pointer again. Since we matched 4 more characters, we're just going to going to take I and add 4 to it now. So now I is going to be at 8, and 8 happens to be that exact position right after the end of the string, right? This is where index 8 is. Therefore, we basically know that we were able to match the entire string. Therefore, we know we can return true, right? Once we find a single true, that means we just terminate, we end the function, we can just return true, and the function is done. Now from this example, it might not be super intuitive why we would use a cache, but let's say we had another path in our decision tree that led us to, for example, index I equals 5, right? And let's say we used all 3 decisions in that path, and let's say none of them yielded the correct result, meaning we were not able to word break this string from starting at index 5. So then we would return false from this path, right? And we would want to cache that. We would want to say that, let's say dp of index 5, right? We would want to set that to false. Basically, what we're saying is if we ever reached this same function call, if we ever tried it again, maybe, this decision tree could be really big. Maybe there would be another path from, somewhere over here where we tried index I equals 5 again. In that case, we would want to return false immediately because we saw from here there was no possible way to break it down. Therefore, we don't need to redo all of that work if we, try the same exact thing. So we discovered that our base case is going to be dp of 8 because 8 is the length of the string, basically, is going to be true, right? If we can ever get to that last index, we're going to return true. So what we're going to do is now do the bottom-up approach, right? We're going to go through every single index in reverse order, right? So we would start at the last character, which is position 7, right? And see, can we word break the remainder of this string? And we would try every single word, right? Like neat, does neat match this string? Well, they're not even the same size, right? If we tried to match neat on 4 characters starting from here, we would go out of bounds of this string, right? There's not enough characters. So of course, this is going to be false, right? It wouldn't match neat. It wouldn't match the other 2 words in our dictionary either. And that's obviously going to be true for dp of 6, dp of 5, as well. So both of these are also going to be false, right? Basically, if we started from 6 or if we started from 5, we would not be able to match any of the words in our dictionary. But now if we start here, index 4, so we're now trying to figure out dp of 4, is that true? Well, yes, it is, right? It doesn't match neat, it doesn't match leet, but it does match code. So we are going to set dp of 4 equal to true. So now let's keep doing it until we get to the first character. So now we're going to be trying from dp of 3, right? So starting from this character, are we going to be able to match any of these? Well, none of these words even start with a T, so of course we're not going to be able to match. So dp of 3 is going to be false. What's dp of 2 going to be? It's also going to be false because if we were to start at this character, this E, would we be able to match any of the words in our word dictionary? Of course we would not. And what about this position? If we started here, would we be able to match any of the words in our word dictionary? Again, not. So dp of 3, dp of 2, and dp of 1 are going to be false, meaning we cannot word break this string if we start at any of these 3 positions, basically. Now we're finally at the result that we were looking for, dp of 0. Is dp of 0 going to be true? Well, let's take a look. So we're starting at the first character in the string. Can we match any of the strings? We can't match leet, we can't match code, but neat, it does match this portion of the string starting at index 0. So then the question becomes, we're asking, can we break the entire string starting at index 0? So now since we did match the first 4 characters, we want to know, were we able to match the remainder of the string, right? So we want to know, starting from here, were we able to match this string to words in our word dictionary? Now, this is why we computed this bottom up, right? Because this is index 4, right? Notice how we already computed index 4 over here, right? It's the one that's highlighted in green because it was true. We were able to do it. So basically the equation that we would use for this is going to be dp of 0 plus the length of the word that we were able to match with, and we know the length of the word neat is going to be 4, so basically we can replace this length of the word with 4, so 0 plus 4 is just dp of 4. We know that was true, so we can set dp of 0 equal to true. So this is basically the result, right? This is how we're going to compute it, and this is what we're going to assign dp of 0 to. And once we've done that, we've computed the result. We know we can return true for the overall function. So with that being said, let's jump into the code. So our cache is going to be, let's say, a one-dimensional array, right? Because for every position I in the string s, we are going to have a value. So we're going to initialize this to false. It's going to be the length of the string s plus 1 for our base case. And we are going to initialize our base case. We know that it's the last position, basically the position out of bounds of the string. So the length of s. And we know that's going to be set to true. That's our base case. So now we're going to go through every position I in the length
Right. Oh, if I remember correctly, we're using DP and we're first gonna start in our base case at the edge of the length of the string. And for each length of the string, we're gonna see if it fits over the so basically give the dynamic program array boolean for each but yeah, I still don't understand why it was solved. The tenants, enough faults. I was, mm, yeah, still
Hey,
confusing
enough characters.
because yeah, length plus one, one, two, three, four, five, six, seven, eight. Why do we need a plus one here? Can I ask chat? Why does it need plus one? Then well, use five connect to create chance. Yeah. Okay. Index zero. Why is there a plus one? We're probably gonna start from the end where I am starting from length F going down. Oh,
Hey, incrementer of -1, and we're going to false. It's going to be the length of the string s plus 1 for our base case, and we are going to initialize our base case. We know that it's the last position, basically the position out of bounds of the string, so the length of s, and we know that's going to be set to true. That's our base case. So now we're going to go through every position I in the length of the string, starting at the last index and working our way to the beginning. So that's why I'm using the decrementer of -1, and we're going to go up until.
starting from the length of S I think this is non-inclusive, so starting from the length of S of -1, which is this one, all the way to -1. Right? Let me try how it's visualized. Uh, so it's 8. So visualize for the inside. Yeah, accessible then hello equals. Yeah, it's the index 0, 1, 2, 3, 4. we're handling index to the exports. Okay, choose zero at end. Before that will yeah. This is a question, bro. So, what I'm decrementing it by one.
The beginning of the string. And for each
And for each one, we are supposed to check if the length of if the for each word in the word dictionary
position I, we want to try every single
of each word in word dictionary.
word in our word dictionary and see if the word matches this
So we're gonna first see
portion.
if
So first we have to
the
see
word dot
if
length.
start
So if dp at index length of s minus 1.
starting at position I, the string S even has enough characters for W to be compared to it. So what we're going to do is we're going to check I plus
1
the length of
is I. Well, we're gonna start at 0 plus the length of s.
W, and we want to know is
No. We're supposed to get the length of the w first. So if 0 plus 4,
it less than or equal
if it's less than or equal to length
to the
of
length
n.
of S. If that's the case, then that means there are enough characters in S for us to compare them. So that's exactly what we're going to do. We're going to if this is true, then let's compare. So we want to know if that's true and if S starting at index I
Starting at index I
going up
is
until I plus the length of W.
w.
So basically, let's say W
If
was
equivalent,
3 characters, then we want to know the first 3 characters in S starting at index I, are they exactly equal? If they
okay,
are equal, then we want to know, okay, so dp of
dp
I is going to be
true.
set to dp of I plus the length of W, right? That was the relationship we got, I plus the length of whatever the word happens to be. Now, if we got a way to word break this starting at index I, that means we can basically stop this loop, right? We don't have to look at every single word in the dictionary. If we found at least one way we were able to word break it, then we're going to stop. So basically, if dp of I is true, then we can break out of this for loop and then move on to the next index. So we're going to start basically at the last index, keep going until we've gotten to index 0, and then once we've done that, we know we can actually return that, and that's going to be stored in dp of 0. So believe it or not, that is the entire code, about 10 lines, I think, and this is a pretty efficient solution, as you can see. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot.
So within each word in the word dictionary, I'm gonna check if I the string at index I is less than or equal. Yeah, it's so
Hey
confusing
everyone,
though.
welcome back, and let's write at least one.
If I plus length w. So we're comparing it Starting from, let me try visualizing it. Oh, oh, hell no. Okay, a new one. So the idea here is, let's say the word is oh, dog, food, have an area, dog, and poop. First set the last index of the string to true all of the set false. So for for each, so basically the for loop here is iterating over the last of the string, decrementing up until up until -1, which is non-inclusive, which means it's only till here from the end of the word. Now it's checking and this is I, so that means that also iterate over inside this I, also iterating over the word. So for each word, we check first. So it's checking if the string at index I plus the length of word is less than or equal to the length of the string. So that means it's checking if this index I, no, it's just I plus length of double. Means we start at 0, 0 plus length of double 3. So the length of this word is 3, 0 plus 3 is less than or equal to the length of dog 1, 2, 3, 4, 5, 6, 7, 7. So it's basically checking if, let's say the word is like dog go for 1, 2, 3, 4, 5, 6, 7. Dog. If it is, that means if this ends up as being E, that means it's not a valid word. So it's just checking if the word is valid. And after that, if it's now valid, so it's gonna be put inside the word. And it will fit inside the string, and we can know if it can be separated with a space and to make a word. We then check and so I'm pretty sure if starting from starting at S, starting from I all the way to I I plus one, right? I plus, yeah, I plus 20 probably is equal to the word. So that means, let's say I is now and here. Cool. So that means it's 0, 1. Actually, no, I should be. But I'm not sure. Hmm. Let me ask. Does this mean I start something considered as 0 1 start and 0 shine in front of it? No, 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 no. Oh, okay. So it doesn't actually start at zero. Yeah, I'm tripping. So it skips it basically until it becomes valid. Okay, this one's wrong. Not actually zero. Yeah, because if it was, oh my god, so of course it's not. It's streets. Oh. So now here we're at 6, 1, 2, sure, one, no. So now we're at 3 plus the length of the word tree. It's not valid, so we iterate over quota 3 plus the 4, 7. That means that's valid. With this, we're gonna first check with S, the string starting at this index all the way to this index up until the length of this word, which is 4, 0, 1, 2, 1, 2, 3, 4, I plus 9 plus 12. So that means 1, 0, 1, 2, 3, 3 plus 4, 0, 1, 2, 3, 4, 5, 6, 7. What? Bro, what? Wait. Oh, God, dude. 0, 1, all the way from 9 sheet. 0, 1, 2, 3, 4, 5. Oh my God. Slices. Is it because Saddam uses food surprise? Copper. First. Wrong. 6. Slice some with salmon, salmon, listen, art. Oh, god damn it. That means we're gonna get the dp of index I equals dp index I plus the length of the word.
Compare them. So that's what exactly the length of whatever the word happens to be. Now,
And we can
if we
return.
got a single way to word break this starting at index I, that means we can basically, this is a pretty efficient solution, as you can see.
And we're finally checking if DPI. So that means after you get the full so if DPI, that means if separation. Oh, well, all right, I haven't really paid attention to what is said. Why is this needed?
Keep going until we've gotten happens to be a loop, and then so basically if dp of I is true, we got I plus the length of whatever the word happens to be. Now if we got a single a way to word break this starting at index I, that means we can basically stop this loop, right? We don't have to look at every single word in the dictionary. If we found at least one way we were able to word break it, then we're going to stop. So basically, if dp of I is true, then we can break out of this for loop and then move on to the next index. So we're going to start basically at the last index, keep going until we've gotten to index 0, and then once we've done that, we know we can actually return that, and that's going to be stored in dp of 0. So believe it or not, that is the
What ensure word fits? Yeah, that means this one should be true. So you put it back. Oh my god, bro. It's interesting. Sauce. That index I. Oh, which is cool. And you can see that plus 7. That means that's true. That means we apply the DP of I to be true. That's so cool. But first, store sort of. It's basically checking it. It's already built. It's already valid. If your index I is true, that means we just return and keep moving forward. And we don't need to check other words. And we have to stop checking each word now and just move on. Yep, I get it. Oh, oh my god. Oh gosh.
the remaining is this portion.
Oh. It's almost wow. Australian. Really? Hold up. It's up. Scripted in that, bro. Oh my god, this is gonna turn into this. Just break the loop. Oh, man. Do you have expecting this? Oh my god. Oh my god, you're so annoying. Like, what the hell? Wait, what if we just do this? I mean, there's no difference. See, there's no difference in the positioning of the parentheses. God damn this. Keep trouble. Thanks for watching. Oh my god.